Hi, this is Dr. Remenacker. In this particular video, we are going to start exploring the idea of limits. You may or may not have ever encountered the idea of limits in your mathematical experiences. However, as far as developing the concepts within calculus, you really need limits. Neither derivatives nor integration, the two primary functions in calculus, neither of these can develop without the use of limits. So what we're going to be exploring here and in the next couple of videos is going to continue to play a key role throughout not just Calculus 1, but Calculus 2 and beyond. Okay, so what is the idea of a limit mathematically? If we had a set of numbers, for example, let's say we had the set of numbers 2.4, 2.49, 2.499, 2.4999, you can see a pattern developing here. And while it will never actually achieve the end value that it looks like it's headed toward, and that end value or that limit is 2.5, following this pattern, we will never get to 2.5. We'll just get more and more and more nines in the number. But you can see that that's the value that it's approaching. The idea of a limit is to determine what value are we approaching. Doesn't necessarily mean we'll get there. In some cases, you do actually achieve that end value. In other cases, you just get closer and closer and closer and closer. Let's take a look at a second example. Suppose you had the set of fractions 1/2, and let's say 3/4, 7/8, 15/16, 31/32, and we continued. Following this pattern, you will never achieve the value, the number that this sequence is headed toward. But the idea of a limit is to ask you, where does it look like we're headed? Doesn't mean we'll ever get there, but the question is, where does it look like we are headed? Well, if you look at this set of fractions, it looks like we're getting closer and closer to the value of 1. Okay. In some cases, you're going to be given functions. For example, something like f of x equals 3x plus 4. And the question is, what does the value of this function draw closer to being as the x value gets closer to, I'll just pick a number, 3. So the question is, as x approaches 3, what value does the function approach? Notice in this case, we didn't say anything about actually getting to the number 3, but we're going to get closer and closer to the value 3 and determine what does it look like the function is headed toward. Okay, when we do this, we can solve this one of a couple of ways. One way to handle this is to graph it. And if we graph this function 3x plus 4, it's going to have a slope of 3. It's going to intercept the y-axis at 4. It's going to do something like this. So here's a graph of our function f of x. If we come over to x equals 3, and we come up to here, the question is, what y value do we come closer and closer to achieving? Now, what's going to wind up happening is we're going to come closer and closer to 3. And catch this. Not only will we approach 3 from the left-hand side, so not only will we start at 2 point something or other and get closer and closer to 3, but then we will also approach 3 from the right-hand side. So we'll include values that are larger than 3 and close in on 3. Okay, so if we wanted to evaluate this function and ask what is the limit as x approaches 3 of the function 3x plus 4. Now this notation may be new to you. If it is, this is how we write the limit as x approaches 3 of the function 3x plus 4. One way to look at this is to approach it from a graphical aspect. Okay, as we achieve or take on values that are closer and closer to an x value of 3, the question is what y values are we winding up at? And notice as the x value gets closer and closer to 3, the y value is going to move in closer and closer to a specific value, or it should. Okay, we're going to look at situations where limits don't exist, but for right now, the idea is we're trying to close in on a specific point. One way to look at these is via a graph. Now, the graph allows you to see some overall things, but it does not allow you to see specifics. Graphs are good for general observations, but they are not real useful when you're getting down to specifics. A second way to evaluate this function is by using a table. So what I'm going to do here is I'm going to first put my x values, then I'm going to put my f of x, which is the y values, and because I'm approaching 3, I'm going to approach 3 first from the left. Now sometimes people get kind of confused about this. So if you think about being on a number line and here is 3, here's 2, and here's 4, from the left, as we move closer and closer to 3, we're going to have values of 2.9, 2.99, and values like that. As we approach from the right on that number line, we're going to have values like 3.1, 3.01. And you could continue from either direction, getting numbers that are closer and closer to 3 without actually plugging in the number 3. This can then be evaluated on your calculator. So if you look to the right of the screen, I'm going to turn on the calculator and I'm going to go to y equals. Well, I thought I was turning on the calculator. There we go. Going to go to y equals. And the first thing I'm going to do is I'm going to enter in my function, which is this 3x plus 4. From there, I'm going to go to the table function, which is the blue button, and then table. Once I'm in the table function, I may have stuff laying around from a previous evaluation. I'm just going to press the delete key to get rid of those values. And what I can now do is, using the values on my table, for example, 2.9, I can enter that. 2.99, enter that. And it gives me then corresponding y values. The y values are 12.7, 12.97. So if you take a look here and you continue exploring further, trying to keep the video somewhat short, I don't want to explore too much, it looks like from this side things might be drawing close to a value of 13. We can also, with our calculator, explore values from the other side. So example 3.1, enter, then 3.01, enter. And if you look at these values coming in from the right, we have 13.3 and 13.03. Notice as the x value draws closer to the value of interest, x equals 3, our numbers look like they are approaching 13 again. So from either the left or the right, it looks as though we are approaching a y value of 13. Now, if we go back up to our graph, okay, the question is, what is this y value right here? Okay, which is where we are approaching from either the left or the right. You know how to compute a y value. You just evaluate the function at whatever the x value is, which is going to give us 3 times the x value plus 4, which is 9 plus 4, or 13. So in this case, coming back over to the left-hand side where we're looking at a value for our limit, our limit approaches the value 13. Now it's very important to say that the limit approaches this value because using a limit, you never technically actually put in that value. So we would need to be putting in numbers like 2.9999999 and 3.0000001, okay? However, there is a shortcut that's typically applied, and that idea applies to situations where you have a function that is continuous. Looking to the right on the graph, you can see that the red line describing the function is continuous. It has no breaks, no surprises in it. So if you have a situation where your function is a continuous function, 3x plus 4 is continuous, it's a line, to shortcut all this work, what you can actually do is just substitute in, like we did on the far right-hand side, the value of x, and that will tell us where the limit's going. Okay, so let's consider another example. Let's say we have something like g of x equals x squared plus 1. Okay, so if I'm going to graph this, g of x equals x squared plus 1 is a parabola opening up, intersects the y-axis at 1. Here's my g of x. Notice once again, as with the previous function, this function is continuous. By being continuous, if I pick some value of x, I don't know, let's say 3, and I come in from either the right or the left-hand side, I'm going to either be sliding down the graph to the y value or rising up the graph to the y value. No breaks, no surprises. And what will wind up being the case is the y value that I'm approaching is going to be whatever the x value is we're interested in, squared plus 1, or 10. We can do this once again because we have a continuous function. I'm going to show you some functions that aren't continuous here in a bit, but for right now, realize that with a continuous function, things are actually pretty nice to work with. If you want to evaluate this using a table, you can do that as well. We can look at our x values, and we can look at our g of x values. Okay, so on my calculator, I first need to come over to y equals. So I'm working over here on the calculator now. I'm going to delete that function. And I'm going to substitute in now my new function, which is going to be x squared plus 1. So there's my function. And I'm going to go to the table function. And I'm going to press delete to get rid of all my old values. In this case, I want to approach, tell you what, let's make this different. Let's say we want to do the limit as x approaches 1 of g of x. So what I'm going to do is I want to evaluate where is the function going as the x value gets close to a value of 1. Well, if I'm getting close to 1, I want to think about the number line. And I have my value 1, that's the value of interest. And if I come in from the left side, I'm going to be using numbers like 0.9. So I'll put 0.9, 0.99. Then I'll also be moving in from the right-hand side, which is slightly bigger than 1, so that's going to be 1.1, but getting closer to the value 1, okay? And as with the previous one, I'm just using a couple of values. If you're working with a more complex function, you may want to use more entries. However, for this one, all I'm going to do is on my calculator, I'm going to put in the 0.9, the 0.99, and that gives me some values. So it looks like here it's 1.81, 1.9801. From this side, just based on this small number of options, looks like I might be getting close to 2. Then what I'm going to do is I'm going to enter numbers from the other side. I'm going to put in the 1.1, enter. I'm going to put in 1.01, enter. let me try that again, 1.01. There we go. Enter. And you can see now that at 1.1, the value is 2.21. And at 1.01, it's 2.0201 as the values get closer to a value of 1. Okay, it looks like once again we're headed to this same value, 2. As with the previous example, from the graph we can see that this is actually a continuous function, so it is legal to go ahead and evaluate the function at the x value we're interested in, and we actually do get a value of 2, the same value that is supported by the table evaluation of the function. Let's take a look at something a little bit different. Let's say that we do something like this. Let's say we have k of x equals the sine of x over x. Okay, that looks pretty ugly. That's probably not going to be one that you're going to be able to graph. Not easily. And let's take this a little bit further. Let's say we want to know what is the limit as x approaches 0 of the sine of x over x. Now, right away, you should know there's a problem here because we cannot substitute the value x equals 0 into this function because it'll give us sine over 0. And you can't have, or fractions that have 0 in the denominator aren't defined. So the way that we're going to need to evaluate this particular limit is by using the table. So the question is, what's this going to evaluate to be? I'm going to choose some x values. Going to evaluate my function and record the results. Now what I want to do first is to go on my calculator. I'm going to quit what I'm at now. I'm going to go to mode. Now on mode, I'm looking at the third line. I want to make sure that this calculator is functioning in radians. The entire time that you are in calculus, make sure that your calculator is set on radians. We will always work in radians. The trick is if you have a physics course that you're working on at the same time, physics is going to want degrees. So make sure that you've got the correct unit that you're working with. Okay, so that looks fine. I'm going to go ahead and press y equals. I'm going to press clear, get rid of that. And I'm going to do the sine of x divided by x. There's my function. Then I'm going to go to table. I don't need these values, so I'm going to go ahead and clear them. Well, hopefully I'm going to go ahead and clear them. There we go. Before I start entering values in or deciding on my table what values I want to use, to protect myself from making a mistake and head in the wrong direction, I'm going to draw a number line. The value I'm interested in is 0. To the left is -1. To the right is +1. From the left-hand side, I want values that are negative but are getting closer to 0. Values that are negative but getting closer to 0 are things like -0.1, -0.01, -0.001. Notice this time I'm using a few more numbers. Going back to my number line, as I approach from the right-hand side, I'm coming in from the positive. So I can use things like 0.1, 0.01, 0.001. We definitely need to use a table this time because, as I pointed out earlier, we can't plug a 0 in for x. The function is undefined there. Okay, so we can't just do a quick algebraic evaluation of the situation. Okay, so I've got some values set up on my graph or on my table. I'm going to go ahead and put in -0.1, enter. Then I'm going to do -0.01, enter. Then I'm going to do negative 0.001, enter. And this may surprise you. Look where the values are headed. We're going to 0.9983, 0.9999, and then here it says going to 1. That might be of surprise to you, or you may not have had any idea where this was actually headed. Okay, so from the left-hand side, that's an important term. As I'm coming in from the left-hand side, the value is headed toward 1. Now, if you're not sure of that, you can plug in a few more values, getting them closer and closer to x equals 0, and you'll see that it does report back results at 1. Next thing I'm going to do is I'm going to go from the right-hand side. So I'm going to substitute in 0.1, 0.01, and 0.001. And let's see what happens here. From this side, I have the 0.9983, 0.9999, and 1. So from either side, as the x value draws closer to 0, the value of the function draws closer to being 1. So the limit of this particular function would be 1. Okay, let's take a look at another example. Let's say we have something like this. Going to use a rational function this time. Let's say we have something like p of x is equal to x squared minus 1 over x minus 1. Now, notice the numerator here will factor. This is actually an x plus 1 times x minus 1 over x minus 1. Okay, this is a removable singularity, or in other words, if we wanted to, we could cancel the x minus 1's, leaving us with the function x plus 1. X plus 1 is a linear function, just a straight line. However, our original function is this x squared minus 1 over x minus 1. In its original form, which is the function we're working with, the domain is going to be all x values, okay, from negative infinity to 1, along with 1 to infinity. You cannot use the value x equals 1 because you'll get a 0 in the denominator and the function's undefined. However, when we graph this, you wind up with a function that behaves like x plus 1. Remember, the x minus 1's can be seen as canceling. Algebraically, they can cancel, and you get a graph like this with a hole in it at x equals 1. Okay. The graph looks like the x plus 1 because the x minus 1's cancel. So what you have is a graph with a slope of 1 and a y-intercept of 1. However, the original function has the x minus 1 in the denominator, which then results in a domain where we're not allowed to use the value of x equals 1. So the graph that we actually get is going to be this graph with a hole in it. If we evaluate the limit of p of x, this function, as x approaches 1. Remember, the limit indicates that we never actually get to the value x equals 1. We just get closer and closer and closer. So what we can do here is we can consider moving in on this function from the left-hand side and from the right-hand side. And the question is, as we do that, what are the y values that we get? Well, the y values that we're going to get, okay, can be once again evaluated using a table, just as we did in the last two. So we can set up our table down here. with my x values and my p of x values. If I set up a number line, I'm interested in getting closer to 1, so I'm going to be coming in from the 0 and from the 2 side. If I'm coming in from the negative side, the left side, a value that's close is 0.9 or 0.99. If I'm moving in from the right-hand side, a value that could be considered would be something like 1.1 or 1.01. As we've done previously, I'm now going to go to the calculator. I'm going to clear my y value, and I'm going to enter in this new y value, which is going to be the x squared, subtract 1, and that's divided by, and we're going to do parentheses, the x minus 1. Close the parentheses once again. Then I'm going to go to table, and I'm going to delete these values. Okay, so using the numbers I've indicated on my table in the lower right corner of the screen, I'm going to use the 0.9, enter, do 0.99, so I have my values there. Coming in from the left-hand side, it looks like I'm going to 1.9 and 1.99. If we were to continue this, it looks from this side like we're headed to the value 2. Now, moving in from the right-hand side, we're going to use something like 1.1 and 1.01. Coming in from that side, we have 2.1 and 2.01. Once again, it looks like we're headed to a value of 2. The interesting thing here is coming in from either the left or the right, we're headed to 2, so the value of the limit is actually 2. Notice here the limit can have a value even though the function itself does not have a value at the number of interest. Okay. Our number of interest here is x equals 1. If you try to substitute that into the original function, it's not going to work. Okay, you're going to get a 0 in the denominator, undefined. That's a problem. Let's take a look at another function. We're going to look at some stepwise functions. Stepwise means that the function is different based on the value of x. You'll see things like this in the business world. If you buy 0 to 10 or 0 to 9 of a particular item, you pay one price, but you get a discount if you buy 10 or more. That's a stepwise function. When you are mailing or shipping a package, there are weight limits. If it's under a pound, it's a given weight. If it's between 1 and 2 pounds, it's another weight. If it's between 2 and 3 pounds, it's another weight. That's stepwise. What happens is your number of interest increases, you're playing by different rules. Okay, let's consider a function like this. Let's say we have r of x is equal to 3x plus 1 when x is less than 2, and it's equal to, let's say 4x plus 2 if x is greater than or equal to 2. We can first graph this to get some idea of what we're dealing with. When we go to graph this, the first thing we're going to do is we're going to graph 3x plus 1. Now, notice this first function only applies to values less than 2. So this is going to give us something that looks like this. There's an intercept of 1. And let's say the x value is right here at 2. I'm going to put a dot there, an open dot, because we're not allowed to actually use that function at x equals 2. Then I'm going to graph the function on the second part, x greater than or equal to 2. Well, that's going to be 4x plus 2. It's going to be a steeper line, and it's going to wind up being something more like this. Okay, I'm sketching in the whole thing, but in reality, we don't want the whole thing. We just want to start at a value of 2, and it's going to be slightly steeper like that. Okay, let's consider several different limits. Let's say that we're going to look at the limit as x approaches 1 of r of x. If we're looking at x approaches 1, okay, x approaches 1 is going to be right there. Okay, notice that's going to put us there on the line. Around that point, it's continuous. There are no breaks. Because it's continuous, we can, as we talked about earlier, evaluate this limit using the function appropriate for that particular value. So it's going to give us a value of 4. If we do something like the limit as x approaches 5 of r of x, as we move in on x equals 5, 5 is on the graph way over here to the right, which is going to take us somewhere up in there. Around that point, the function is continuous. Just as we did with the limit we evaluated a few moments ago, we can evaluate this limit using the function that is appropriately defined for that range of x value. Just plug the numbers in because it's continuous, and what this will give us is 22. There is, however, a third situation. And this situation is the limit as x approaches 2 of r of x. Now, in this case, we have a problem. Our problem is if we come in from the left side. Okay, so if we come in from the left side, we're going to be on this particular line, and we're going to be headed here. Okay, so if we use numbers like 1.9, 1.99, it's going to bring us in on that red line. If, however, we use numbers like 2.1 and 2.01, getting closer and closer to 2 from the green side, it's going to take us to this value. We're headed to 2 different locations. We are headed to 2 different values depending on if we come in from the right or the left side. In that scenario, we wind up with 2 different values. Here's something you may not have seen before. When you're heading in to 2 different values, your final answer is undefined or it does not exist. It is completely legitimate for a limit to not have a value at a particular point because coming in from the left sends you in one direction, coming in from the right leads you to a completely different location. Okay? So coming up with solutions for limits where it's undefined is a reasonable thing. One last concept I want to take a look at in this video, and that's the idea of limits at infinity. Infinity is a concept that we are going to be using, especially when we are doing integral calculus, which is next semester. So we need to get a handle on how we're going to be using limits at infinity. When you are working with limits at infinity, okay, what you can wind up doing is, let's say we have something like, let's say g of x is equal to 1 over x. Okay, so we have our function, And then if we evaluate the limit as x approaches infinity, okay, let's think about what that's going to look like as far as a graph goes. There's that. If we graph 1 over x, 1 over x does something like this. And if you think about this, if we do our limit of g of x as x approaches infinity, looking at our graph to the far right-hand side, that graph runs asymptotic to the x-axis. In other words, it gets closer and closer and closer and closer to 0. Because we're talking about a limit, we don't actually have to ever get there. You can't get to infinity. Okay. So what winds up being the case is the limit approaches 0. If we take a look at a second situation here, let's say we have something like this, h of x equals 3x minus 5 over x minus 3. When we graph this, what's going to wind up being the case is we're going to have a horizontal asymptote at 3. And at x equals 3, this thing is undefined because 3 is not in the domain of the function, so there's a vertical asymptote there. And what this graph is going to do is something like this. Remember, the horizontal asymptote causes the function to level off at that asymptote as x goes to infinity. Now, in this case, if we do this limit of h of x as x approaches infinity, what'll wind up being the case is we're going to look at the far right-hand side, and you can see that it's leveling out and getting closer and closer to a y value of 3. Does it ever actually achieve a value of 3? No, but the idea of a limit is not getting there, but the question is, what does it look like we're getting closer and closer and closer to achieving? Okay. We're going to talk more about this idea of rational functions being a polynomial where you have something going on in the denominator. And we're going to talk about these ideas as x goes to infinity in the next video in greater depth.